Well, it is the top of the hour, so I say we get things going here. My name is Annie Burgess. I'm the lab director at ESIP, and I'm the room host for this session. Just a few friendly reminders to stay on mute while presentation is happening. We'd love to see faces during any discussion time and when we're not in a direct presentation. So we invite everyone to turn your cameras on to say hi if you'd like to. Hi there. Also, just a reminder on the bottom bar of your Zoom, to familiarize yourself there. That's where you can add reactions if you like something that one of our presenters is saying. You're also able to raise your hand. And so just reminder to check that out at the bottom. Also a reminder, in the Kiko chat space at the top of the notes is our ESIP code of conduct. So if you haven't checked that out, please do. And lastly, that we will try to capture 3 takeaways from this session. So keep that in the back of your mind as we move along. So with that, I will turn it over to Johan. Johan, take it away.
Thanks, Annie. Hello, everyone. Thank you for joining our machine learning tutorial session. And this session comes out from our 2019 Funding Friday project. So, and this year's Funding Friday idea pitch is, well, as idea gathering is this Friday. So tomorrow, if you are interested, please feel free to join your colleagues there. And I'm going to start sharing my screen. Can you all see my screen okay?
Yes.
Okay, great. And Anne and Nancy and Annie and Ben, if you can help me monitor the chat or let me know if there's any questions, that would be great. Thanks. I'm gonna present mode. Did you see the present mode?
Yes,
okay.
I believe so, yes.
All right. So
Johan, I'm still seeing your slide, your I'm seeing your full PowerPoint interface.
That would be aggressive, but I'm gonna, okay, let me try another, share my screen. And
nice sunset photo.
Nope.
Bingo.
Yeah, there you go.
Right. Okay. So here's just a quick roadmap for today that we will brief review what we have done and our original idea from the Funding Friday in the summer meeting 2019. And after that, I'm going to take a Slido break to get some background information from our attendees. With that, I'm going to move into the brief overview of the machine learning, and then we'll move on those interactive session where you can try out the tutorials. Today, I'm going to focus only on classification because there are a lot of contents in there. So that might take a while for people to go through it. And I already put the link to the tutorial in our Sketch webpage and also in our notes document in the Kiko chat. So you can go find that link and open it. And after that, we will have a Slido break, the second Slido break, to get some feedback from you and also gather some future plans that we might work on in the next year or two. So on the left is our Funding Friday poster proposal that what we try to do. That's when everything started like a year ago. So if you look at those posters, what we are trying to do is to collaborate between the machine learning class and the data management training clearinghouse to put together 3 machine learning tutorials. And we fortunately to get funded through the ESIP Funding Friday. And to get into more detail that what we want to do is to build those tutorials depending on the open source software, including both Python and R. And it's like earth science application oriented and to assist our development. So we have the clear focus on earth science applications instead of those like computer science based tutorials. And we want to provide publicly accessible and catalog information through the DMT clearinghouse. And there's nothing wrong with those existing computer science tutorials that to classify like cats and dogs based on pictures. But there's some more, I think those tutorials can be made more engaging if we are focusing on earth science applications, since we are focusing, we're targeting towards earth science communities. Don't get me wrong, I like those cute cats and dog pictures, but just not, it's not that most useful thing for the earth science community. One thing is that our earth science data has some really unique features that those computer science images do not have. For example, we have a lot of spatial autocorrelation as well as temporal autocorrelation. Those tutorials do not cover how we can address those issues. And if we do not take care of those, that can lead to some problem for our earth science applications. So what I want to see, or what I think the earth science community want to see, is that tutorials focusing on those earth science phenomena, such as flooding and drought extreme events, and then try to use those earth science problems, develop those tutorials so people can be more engaged and get more used to how we apply machine learning models to earth science problems. So this is what we have done in the machine learning cluster. We built a tutorial, and it's as promised that we're built upon those open source software and platforms. So the two major components is R and Python, as well as the Jupyter Notebook. And this one is the Google Colab, which is the Google Cloud service where people can share the code for teaching and learning. And then the right one is the MindBinder project, which is funded through Google Cloud, as well as the Turing Institute, where people can share different coding experience and as a teaching resource as well. So this lab is a screenshot of the GitHub repo that has the description of what our tutorial is about and the instruction on how to use tutorial. And if you go to that page, which is in the node documents, you can see those like buttons of launch binder, and also open in Colab, which will directly take you into the notebook, and where there's interactive sessions you can sort of play around. I want to just remind you that the binder project might take a slightly longer to load. So sometimes it might take like half minute to a minute. So if you are going to the notebook, that would be, I would remind you to be a little bit patient. Don't refresh your page too frequently. So some people has a lot of argument about whether using R or Python, but for me, I was trained as a statistician. So R is basically my native language when it comes to programming. So R has always been my go-to choice. But there are a lot of, I now also start to adopting Python because they are really well developed for geoscience applications with all those ecosystems for the geoscience data. So, and R and Python can be really well working together, especially R has a lot of statistical capability, which are not currently available in Python. So I've always been trying to combine those two all together. So there's some neat way to combine them together, such as using the Jupyter Notebook that you can use both Python and R. And you can also using RStudio, R Notebook, which you can also use both Python and R, and some other software such as Julia, which is really rapidly becoming popular among programmers. And on the right side, I shared an article, which is the R and Python and Love Story, which is really a nice read. I echo a lot of the statements in this article a lot. So I've been using R and Python a lot, and I advocate everyone try. If you are R user, try out the Python. If you're a Python user, then you should try out R as well. So this is just really quick overview. Also serve as a platform, as a stage where we can wait people to juggle into this room. And now I'm gonna take a Slido break, and you can see this Slido code here. Also, if you want to just scan the QR code on the screen, you can also go in there too. Let me bring up the Slido, and we are going to Slido room 1, present mode. And hope everyone can already get into the Slido. I'm gonna start the poll just in a minute. If my internet cooperates. There we go. So there will be 3 questions, and the first 2 are multiple choice, and then the last one is a word cloud. You should see the first question already. So I just want to, this first question want to know what's your level of experience with machine learning, and that will decide how I want to go into details for some slides in the later. I'm gonna wait for maybe a minute or 2, so let people to complete this. And we have 37 people right now, so I hope that more people can participate in this poll. That would, as I said, that would be helping me deciding like how detailed I want to go into some like later slices. 6 people. Okay, I'm gonna try to reach like 12 people. Let's see if we can double the size. Nine. Come on, we need 3 more.
Yuhan, people are having trouble getting to the Slido.
What do you mean
Oops.
having trouble?
People are looking for a direct link.
Oh, it's just Slido.com. If you
Slido.com. I
Yeah,
said
and
the wrong thing in my.
if you use Slido.com and then put in the code ESIP ML, both capital and the number 1, that's the code for our current pool. Okay, we got, yes. I think people now are getting into the Slido. Great, we have, I'm gonna wait for half more minute to see if we have like more. And it looks like that we have most people that have the concept but haven't used it at all, haven't used it before. And there are also some people have no experience with machine learning at all. And we also have some people, minority, that know how to apply machine learning model to my work, to their work. Great, and we have 30 people. Great, thanks. I think I'm going to move on to next question now. So which is, what open source programming language are you comfortable with using? Like R, Python, Julia, or none of the above? Or want to learn, or you just don't care about those programming? You just want to know high level, which is fair. A lot of managers don't really need to know the programming. So that's why during our design of the tutorial, we're also trying to provide some background information. Hey, Annie, can you help me mute other speaker at this moment?
You bet. I'll mute everyone and then you just unmute.
Okay, great, thanks. Okay, I'm gonna give like half more minute. So most people are comfortable with using Python, and some of you are comfortable with R, and some of you haven't used any of those before. So in our tutorial, we provide both Python and R. In R, you can also use in RStudio or in Jupyter Notebook. There are different options you can choose. So which like mostly suitable for you, you can choose that. Okay, I'm gonna stop for this one. I'm going to move on to our last question for the poll. Is what type of machine learning applications or models are you interested in? If you're interested in classification, regression, or anomaly detection, a neural network, random forest, or deep learning. So just put short phrases, don't put a whole sentence. We're trying to have a word cloud here to see what's going on. There's just examples. You don't need to like follow those examples. If you have anything that you heard that think might be helpful, that can also put it in. So in the future development, we can try to incorporate those into our tutorials. Neural network classification are the most dominant one right here. Oh, some people also interested in natural language processing, which is, I think that can be really helpful for those like archive or the data repository, like discovery. That can be a really important, really useful ones. I like people putting all. Yeah, and we want to know all about those. So I'm gonna wait to the 30 or maybe 25, and then we can move on for our later presentations. And let me take a screenshot before I forgot. So great. Thanks for everyone who participated in this Google, in this Slido pool. And there's a really important information that can help us for the future developments. I'm gonna close the pool now. And thank you again. So this is our first Slido pool. And at the beginning that I give you a quick overview of what our Funding Friday project is about. It's about building those tutorials. And since some of you mentioned you have the concept, but do not know a lot about it. So I'm going to provide about 10 to 15 minute brief overview of machine learning and some important background information for the tutorial. And then after that, I'm going to move on to the tutorial demonstration. So this slide is just showing the history of the artificial intelligence and the machine learning developments in all the scientific disciplines. So it's all started with computer science. So the artificial intelligence, that term was coined in the in 1950s. And then since 1980s, the machine learning become emerged, and a lot of like algorithms are developed since then, like the classification and regression regression tree, and then there's also the neural network as well as the support vector machine that are all developed really in the 80s and like 90s. And since the 20s, that machine learning has been starting to apply into different scientific disciplines. And it started with the computer vision, and then now it moved into the earth science and has been exploding. All different scientific agencies, federal agencies, as well as the academics are trying to use machine learning to solve a lot of scientific questions. Just as a plug, that we have a panel discussion on next Tuesday, which I believe is July 21st, that we are discussing the organizational strategy on the adopting machine learning and artificial intelligence for advancing earth sciences. We have panelists from both NOAA, USGS, as well as the Microsoft and Element 84 and University of Maryland to talk about this topic. And we will also chart the next chapter of machine learning cluster within ESIP. And in the year around 2010, that's when the deep learning started to exploding into the scientific field. And it first started as a way to compress the feature in your image using a lossless way, but now it has been applied to more field, and such as those pattern recognition for those extreme weathers in earth science, that there's a lot of like ongoing active research on those. To me, that machine learning or artificial intelligence, it's all driven by the problems. So that's why I put the Earth in the center for our own application, which is the machine learning for earth science applications, that it's always driven by some problems in earth science, where we have three major components surrounding that. One is the data, one is the model, and then one is the production system, especially when you try to do those large scale applications. So the driver for the whole thing is the problem. So I try to connect this four major components into automatic vehicle, into a car. So the driver for the car is basically this problem driving the whole application. And then the feel for the car is just the data we have to solve the problem, because without the data, that machine learning, basically there's no way that you can use machine learning. One of the reasons that machine learning has been exploding in the past 2 decades is just because the increasing amount of data that are available to the researchers. And the engine for a car, for the machine learning, the vehicle of machine learning is basically the model. So you have all different models. That's the different engines you can put into a car. And some model works best for a small size car. Some model works best for a larger size car. And then the last one is the frame of the car. It's basically the production system, that how robust your operating system, your production system is, and how you can connect your data to the downstream to make some impactful applications. So that's my personal understanding of how we use machine learning in earth science. It's always driven by the problems. And on the left side, that shows a survey for a lot of people who are using data science and computers and machine learning. They're just showing the time that they spend on different components of machine learning applications. Like, as you can see, that majority of the time have been spent on the wrangling of the data, and also how you put all different pieces all together for those machine learning applications. And a right side is XKCD comic that just describing people's impression, or sometimes people who have not used machine learning before, how machine learning looks like. Basically, you have the data and just shake your model, shake your parameters, and to get your final outputs of your model. That's the thing that frustrates me the most when I first switched from statistics to earth science. Just like when I see people using, sometimes becomes abusing those statistical methods, I get frustrated. So I want to help people to better apply those methods in a correct way. That's one of the reasons why I want to take this task of creating those tutorials. So for machine learning, there are different types of models. The first one is the supervised learning, where you basically have a lot of involvements as a user or as a developer of this model, that you have the raw data, and then with your you will have interaction with the data. You try to label this data if we're talking about classification problems, and with the interaction between you and the data, you create an algorithm and then feed into a processing pipeline, and to create those output, either it's regression or classification. This is the supervised learning, there where you have active engaged role in the development of this model. Where the other type of model is the unsupervised learning, where you have the same input raw data, but you just directly let the model to interpret the data for you. So that can be clustering, so separating them into different clusters based on their input features, or it can be that you want to detect anomaly without like human intervention of those. That's become super popular in a lot of data archive, try to do the automatic quality flag of those data. So there are like three, I personally categorize them into three types of applications. One, for the unsupervised, there's like clustering or anomaly detection, where you do not have the prior knowledge or do not have active engagement from the developer, separate them into two parts. For here, it's like separate them into different clusters. So as a way to help you to, as a first step, to interpret your data. But then for the supervised, is that you provide instruction to the model. For example, you know that you want to classify all your data into multiple classes, like the two classes in this center figure, that you have the orange cluster and you have the blue cluster. And the other type of supervised, that you instruct this model to find a relationship, association between the input and output. That can be a linear relationship, can also be non-linear relationship. And for machine learning, that if you're trying to, it's like too powerful to do a linear regression. So most of the times people are using it to identify those non-linear relationships. So in the data component, that you have different ways to collecting the data. You can use those existing data, basically those like secondary data from the archives, like the National Center for Environmental Information, where I'm working with through the Cooperative Institutes. And the second type is self-collecting data. And then the last one is the synthetic data. For the existing data, that is really easy to access and also provide comprehensive data. But you might spend a large effort to process data, and then you can have a sample bias depending on how the data is collected. For the self-collected data, that you can tailor the data collection, and then through those controlled experiments, you might get like more balanced data, but it can be like resource intensive, as well as you can only get those limited data because the resource limitation. And you need to really carefully design your data collection method, otherwise you have those sampling biases. The synthetic data is basically, it's really easy. Oh, I would not say easy, but it's reproducible because it's mostly generated through computer codes, and then it's easy to control. But it can be computationally expensive. For example, for me, I do a lot of radiative transfer simulation, which can be really time intensive in terms to generating those simulations. And then the data you generate can sometimes be actually different from the real data that you might apply your model to. So that can be a concern. So there are some implications for the data and the AI ethics when we are talking about data, which on the left side is one of the story I recently heard. It's basically about how the data bias can lead to unintentional or implicit bias in the final applications. This one is the statement that those automatic faucets are racist, because the automatic faucets are developed in the 60s, 70s, where the data sample they use to developing those technology are mostly focused on like light skin or like white people. But for the people with color, that when they try to use this automatic facets can have like really bad feedback to the people who are developing it, because it just not work for them. I found this like so very fascinating, and there are a lot of discussion in the AI and machine learning world about the ethics and how we try to avoid those biases in the data and in the model, in the technology itself. And speaking for the data for earth sciences, this is one of the classic example I want to use is the weather station across the global land area, where you have a lot of data clustered in the North America, clustered in Europe, but where you have a lot of those data desert in South America, in Africa, in central part of Australia, as well as in Central Asia. If you try to use this in situ measurements, the weather station measurements, to build your model, to train your model, you need to really be carefully thinking about how your model might be biased towards those data intense regions. The implication might be that your model might perform worse for those regions where you do not have data, and that can have implications for decision making, such as the climate change adaptation. If a lot of people are trying to use AI for climate sciences, that we really need to care about the Africa continent. And recently, there's some data call from foundations trying to fill in the data gap within the African continent, which is really important components. Oops. So once we have the data, that usually that you want to do is to extract the feature from your existing data. So for earth science data, we usually have like space and time component of data. And also if you have different locations, that becomes really high dimensional. And if we're talking about satellite images, which is the one that I'm working with, that you have multiple channels, so it just like multiplies the dimension you will have in your data. And first thing you will do is try to extract those most important feature for your application, try to avoid those curves of the high dimensionality, because it's not always that including more feature will give you better performances. And once you have the data, you have the feature, and you move on to the data, to the model selection. And I think the model is linked to all different components, which is the first is problem. What different problems you have decides what model you will choose. Either it's classification or regression, or if you're doing unsupervised, like the anomaly detection for your quality control, the first step quality control for the data. And then you will have the sample size. Your sample size would also dictate what data you might have, or what model you might want to use. There are some large sample size will have like some model performs better, but there are also imbalanced samples. For example, there's those rare case scenarios, those rare events such as hurricane, that naturally you will have imbalanced samples. How you address those imbalanced samples in your model development is something you also need to consider for selecting the model. The last part is the feature, that how many different features you have, and do you have any special features, like you have like spatial and temporal components in the feature. That also dictates what model you can choose. Some really recent study have been really focused on incorporating those spatial and temporal features in earth science problems that can significantly improve the performance of the machine learning models for those earth science applications. And with the model selection, and you can train your model and then move on to next stage, that for when you are evaluating your model, you want to avoid those overfitting or underfitting of your model. For example, when we're talking about regression, that if you have a data points shaped like this, you don't want the left case, you don't want the right case, you just want the just right case. And sometimes that for the people who are doing machine learning or doing model developments, we more think it's kind of like art instead of science, because there are a lot moving pieces that are changing at the same time. So there requires a lot of like back and forth iterations of the model development. So same thing for the classification, that you do not want to have a really simple model that do not perform very well. Also, you do not want to have a too complicated model, which can lead to overfitting, where it's really just tailored towards the data on your hands. When you try to apply it to the real world, those like new data, then everything just falls apart. That's something you want to avoid for the classification, the overfitting. When we are talking about overfitting, underfitting, it's always a bias and variance trade-off. So assuming that this targets in the center is the optimum model, that and the whole target space is the possible model space, and the bias describes how well the one model can proxy the optimal model, and then the variance describes how sensitive that our model are to our training data set. If you change a set of training data, does your model performance change significantly? If so, that means you have really high variance in your model. And what you want to do is to balance in the bias and the variance. That's because when you have more complicated model, when you increase your model complexity, that your bias typically decreases. But at the meantime, when you have really complicated models, that a lot of things are changing unexpectedly. So that's why your model variance will increase dramatically when your model complexity increasing. So the total model error usually is a combination of the model bias and model variance. You want to find those optimum model complexity for your model development. That's where you have the minimizing your total errors. To do so, you usually try to separate your data into training and testing. So the testing data you always hold out to assess your model performance. And with the model complexity decreasing, that your training error will start increasing, but your testing error will decrease because you start avoiding those overfitting issues. So you want to find those optimal errors for your model development. So on the left side will be you have like low training errors, but you have really high testing errors. That's when you know you have those overfitting problems. On the right side of this figure, where you have both testing error and training error are really high beyond those acceptable range, then you reach to an area where it's underfitting. So you know your model is too simple. You want to start to bring more moving pieces into your model to increase the complexity of your model, to find those optimum areas. So in order to do that, in the tutorial, you will learn how to do the cross-validation with your data. So cross-validation, what we try to do is that when you have overall, you have a data set. first of all, you want to separate them into two groups. The first group is the model for model development and selection. And usually within that model development and selection, you will further separate them into training and validation. And in the meantime, you also set aside an independent evaluation data set. So this one is usually called the testing data set. This one you will never touch when you're doing your model development. But this is like really traditional, typical way to do it, traditional way to do it. But now, because the computational power is really easy to implement something like the cross-validation, so people are because if you only do one iteration of the training and validation separation, sometimes your model might be sensitive to your training data because you might have like high variance. So what now people are trying to do to iterate it multiple times to make sure that the average performance of the model in certain complexity performs best. So it's not just simple model, it's like average across multiple times when you train the model that try to reduce the variance of your model. So basically what you will do is to separate your development data set into multiple folds. And this is the classic k-fold cross-validation. There are like multiple variations to this k-fold cross-validation. I have pointed you to some external links in the tutorial. So within each iteration, each row here that you hold out, which is the data set set here as green, you set aside fold one, and then you use the rest of the data to do the model development. And then you evaluate this model based on the holdout data set. And you repeat it multiple times, and then you get the average performance of each parameter setting, and then to decide which parameter you want to choose for it. And meanwhile, that we still do not touch the testing data set. So the testing data is always there independently, only when we decide what's our final model, and then we will go to the testing data, try to evaluate it. So that's why I sometimes get frustrated when I was reviewing those machine learning papers that they do not really understand the testing data set need to be set aside. And so there's some cross contamination of the model training and also the model evaluation. So that is just a really quick overview and on the machine learning background. Now we can move on to the tutorial itself. So what I'm going to do is to share how you get there. So if you can copy this link into your browser, or you go to the Kiko chat where I put the link there. And it's also on our sketch page, I believe. So here's a link to the tutorial. So even if you finish the training today, you want to go back, you can always go to this a link on our sketch page. Also, I've put the slides on the sketch page as well. So in case you find some slides or the background information useful for you. So here is my GitHub repo for the machine learning the class tutorials, where here I describe the background and how why we developed this machine learning. And here are the instructions on how you can access the machine learning tutorials. And today I intentionally removed the regression notebook. I want everyone to focus on the classification, so there's not too many moving pieces that I cannot answer all those questions. So if you are a R user, what you can do is either click the launch binder for the RStudio environment, or you can, oops, that I should like open it in another window. Let me redo it. And yeah, if you click the launch binder link, it will start to establishing this binder virtual environment for you. So you'll see those roaming circles there, and will take about half minute to a minute most of the time. Sometimes you might need to refresh it if you have been there for about like 5 minutes. If you are 5 minutes, then maybe you exit and re-enter it. And if you are more comfortable with Jupyter environment, but still want to using R, still want to learn R, I recommend you to click the second button, which is using the Jupyter Notebook workspace virtual environment, but still implementing the R tutorial there. So here I already have the RStudio environments established. I'm going to go through each of them quickly, and you don't need to go through all three of them. But if you are a Jupyter Notebook and Python user, then you click this button, open in Colab, which will lead you to the tutorial on the Google Colab. So for the RStudio, that you need to click on this classification button, a classification folder on your right bottom of your screen. So I'm going to go through the RStudio environment first. So the classification, if you go into that folder, where you can see that there's the host, that's all the notebook that you have here. For the RStudio, you can only use this one, the file ended with RMD, which is R Markdown file. And if you click that, RStudio will automatically load this notebook for you, which gives you a detailed instruction on how you can run this notebook. And so that whole notebook started with the introduction of what this purpose of the tutorial and the learning outcome of our tutorial. The first for this classification one is to understand basic workflow of how you do a machine learning classification application. And then you can implement, hopefully you can implement a basic classification workflow using R or Python after going through the tutorial. And the third one is that interpret the results of the basic classification applications, such as using confusion metrics and other things. And that listed all those tutorial contents that we start with the data set and how you process the data. And you need to load in different libraries in R, where we primarily based on this Carrot data package, which can support 238 machine learning models that's available through R. And that's really powerful. I've been using it. Without this package, my PhD dissertation would be a mess. So highly recommend you check out this package if you're using R and if you want to use R to do machine learning. They have really detailed documentation, so which is this link here. It's also a GitHub page where you have a lot of examples you can follow. And with the library, and then you get into the data, and then you go through it step by step. And since RStudio is not that like user-friendly in terms of the notebook, I'm going to move on to the Jupyter Notebook /R, which is implementing the R in Jupyter Notebook. So in here, where it's the same thing, but just like have a better display of all those components. As I mentioned, that we start with the introduction of our tutorial, and we have the purpose outcome is the same thing, that those two documents should be exactly identical. And the tutorial contents from the data processing goes all the way. The first component is how you process your data, reading your data, and process the data, separating data, and then you start building a model. In here, we introduce both K nearest neighbor, KNN model, which is the most intuitive classification model that I believe that you can find. And then the second one is the random forest, which has been a really common model, have been used by people in atmospheric science in different like earth science fields. The reason that it has been really popular is because that it's really robust given the regular size of the data in earth science, but it might not outperform other models if you have large data set. And here we spend one section just focusing on how we can do the cross-validation, because cross-validation can be tricky. And when you first start to using machine learning and cross-validation, the thing can be confusing. So we have a whole section dedicated how we use cross-validation for our for KNN and for random forest. And then last one, last two components, how if you have two models like KNN and random forest, how you select between those two models. And then the last final step is that comparison between binary classification and multi-class classification, because in a lot of times that you are doing multi-class classification, but you can also convert them into binary classification problems. Try to, there's some like structural design for your model. So in this case, that we are using Landsat data. So here are all those like preloaded results from the R and slash Jupyter Notebook. And so I'm just want to go take you through quickly that this gives you the information of the Landsat data that we're using, that there are 8 channels. We're using the reflectance of these 8 channels, try to classify the area within the Western North Carolina, which is the area where I'm living right now in Asheville. And we have 5 different classes, from forest to corn to soy and urban area, as well as water. So for this 5 class, we get this data from USDA. So what we first try to look at how the data distribution looks like, how many classes we have for each different labels. We have forest slightly less than the other labels. That's by intentional design. I choose the data like this. So, and then we move on to how we first look at the data to see if we can distinguish those, distinguish the data. And this is scatter plots. And then we also, and I want to ask you to try to modify the code to see if you can visualize the data in different combinations to see what might be the best combination to do it. That's one way of feature extraction or feature selection. And since we just started, so I want to show you that how different way of splitting the data, when you try to split in data into training and testing, can affect your distribution. So here, if you do those stratified splitting, you can get exactly the same distribution for your training and testing comparing to your original data, which is on the far left. That's the ideal situation because you want to make sure that the training data you have can represent the real distribution of your data. So this is the relative frequency that we are talking about here. And if we move on to some random splitting, that you might have some data distribution look like this, that it's not too bad, it's not horrible, but it's not ideal because you can have those fluctuation in your sample size that can, if in those extreme cases, that might affect your model performance. Because if you have for example, if you have only 10 samples of forests, if you feed that into your model training, basically the model will try to ignore that class because you have a little number of that sample. So basically, if they completely ignore that sample, they can get pretty much really high accuracy. So you want to avoid those. So we start with our model building in those binary cases. That's because that it just started. So we start with simple things, and we go through how you do the KNN building. And next step is the general how you can calculate the confusion matrix, and the confusion matrix will give you the quantitative information of how your model performs. For example, here we got the overall accuracy for our KNN model as 0.95, which is pretty high quad accuracy because we choose those easy 2 classes. One is forest and one is water. And we move on to random forest and then to the model evaluation. So using the same structure and how you do different model evaluation. So everything, when we are trying to design this tutorial, what we try to do is to make sure this tutorial is really self-explanatory. So you don't need to, you don't really need to have me sit with you. So you have to have somebody to walk you through it. But the notification or the description in the tutorial should be able to walk you through each step. And also you can hide those codes and if you just want to look through those workflows. And now this third section just focuses on the cross-validation of the k-fold cross-validation and how you use the k-fold cross-validation to choose the best parameter for your model. For example, for the KNN, you want to decide the number of neighbors you use for your model. And then the last, apply that to the random forest that you might have more moving pieces. Model becomes more complex. And the last step is the model selection, where you can compare the model between the random forest and the nearest neighbor, k-nearest neighbor, based on your cross-validation results. And we move on. If I go in too quick, I apologize, but I think I just want to walk you through different components of this notebook while you can play with it. So this as a KNN model for the multi-class classification, where I also showcase that how you can do this cross-validation, and then the model performance significantly dropped to 0.65 for the overall accuracy. That's because there are 3 classes: forest, soil, and coin, which 3 are really hard to separate. So when we look at the confusion metrics, that you can see that there's a lot of confusion between corn and soy. So that's something that we need to work on in the future. So you can try to see in this activity here if you can implement random forest model, try to improve the performance of this. And so here is the last Python notebook in the Google Colab space, and apparently it's still loading. Okay. One thing to run it, you have to click on the connect. Otherwise, the Google Colab space will not give you the workspace to go through the tutorial. So once you click the connect, that it gives you, it's allocating the space for you. So the first step here is everything at the beginning is still the same, slightly different on getting the data, because Google Colab do not support, it support either using Google Drive to share the data, or I can clone the GitHub data there. So I basically have one section here to clone all the data. It will ask you, do you want to run this notebook? You can say run it anyway. So it's just getting all the data into your cloud space in the Google Colab, where you get all the data. You look at what data we have here. Now we have the notebook here, and as well as the data, which is label information of different name with color classes. And then we also have the CSV, which is sample data we will work with. And we will read in the data, and this just gives you a spatial image of how the area we're looking at. This gray area is basically the Asheville city area, where you can see all those highways, you can see the water, the French Broad River and other water bodies. And then you have the forests, you have the croplands that are different in the landscape. And now move on that we will use the pandas as a tool to reading our CSV, the comma separated value for the North Carolina Landsat 8 data, and gives us the dimension of our data, which is we have 2,375 samples. And then we try to look at what our data looks like. Now we have the location of our different sample points. We have the class, which is the existing label we got from USDA. We also have the reflectance value, which is not scaled for 6 channels from Landsat 8. And when you move on to next, which you have, because Python is like started with 0, so you want to avoid those confusion where you have one column here started with 1. So we just basically drop this column. So now that's our new column, new data looks like the location class and reflectance for 6 bands. And here gives you a description of how the 6 bands looks like, the central wavelengths and what's their main purpose of the in terms of wavelengths. And we have 5 different classes as listed in this label information file. And then we want to, again, we try to recreate similar things from R. So we try to make those R and Python notebook are consistent with each other. And now we want to plot those feature space. We're looking at 2 bands, 2-dimensional scatter plot here. So the green color is for the forest, and then The purple is for the soil, and then the soil, and then the orange one is for the coal. Yeah, and then the gray is for the urban, and then blue is for the water. So you can see there's some separation, but it's hard to use 2 features to separate 5 classes. But you can try to play around with different combinations from different channels. You have 6 channels there. And then that you can here try to change your code, my code, and try to play around with it. And again, we try to simplify it to 2 classes, which is forest and water, to start with our tutorial model building. So now we simplify them into 2 classes. We start building our first k-nearest neighbor. I'm just walk through, and if you have questions, that let me know if the notebook doesn't work for you. So for the k and n that we have, that first using this scikit-learn to build that data and build a model. And now we want to look at how the model performs. So we generate the confusion matrix. This chunk describes how you can generate confusion matrix and visualize it. Here, that on the left side, just the number of samples classified correctly for forest, and the number of samples classified correctly for the water. And on this diagonal is the number of samples classified incorrectly for different classes. And here, just the percentage of samples that in each category. And then we can try to report out the accuracy of our overall performance and precision of our models, like how precise is for the forest class and how precise is for the water class. And overall accuracy is listed here. There are different indicators you can use to evaluate your model, depending on your final application. So that's for the k-nearest neighbor, which is really straightforward and easy to implement. And k-near, the random forest is ensemble of the model, which you create several like weak, we call it weak classification model. And then you try to combine the final outcome of those weak models. So statistically, you can get more robust and more high performing model than a single strong models. That's the basic concepts of random forest. So you basically generate multiple classification models or regression models if you are doing regression applications. And then you try to combine the final outcome from those multiple, the randomly generated model, and combine the final outcome all together into one. So here we have created a random forest model, and then we try to do the same thing to evaluate the performance of the model, where you have slightly higher performing model because you have one more correctly classified forest samples, because we have like relatively small sample size here, but it's still improvements, you can say. And you can also print out the accuracy indicators, the precisions and other things. And now here, I'm just showcasing some extreme cases of the cross-validation. And also I emphasize the stratified cross-validation, the importance of it. Because if we randomly separating the data into, if we repeat the separation twice, the left side is for the training and then the right side is for the testing, if we do not do the stratified sampling, that on the left side, you can see a lot of variations in the data distribution between forest and water. And you're feeding those data into the model 3 different times, and then your model performance will definitely be different. And then also the same thing for the testing. So you'll get a large variation when large variance when you're trying to do your model without stratify your model, stratify your data based on the class distribution, the real class you have. So now if you do stratified cross-validation, which you separate the data into training and testing based on the percentage of each classes. And what you can do is still repeat it 3 times. And you can see that if you repeat 3 times, it basically follows the same distribution for your training and testing data. So which means that you have really consistent distribution of the data to train or evaluate your model, which is a good thing to make sure your model training is not biased. And that's just fun activity, try to emphasize the importance of stratified data splitting. And now we move on to build the cross-validation. So for the KNN, which is really super fast, and to do that in the Google Colab space. And so it gives us the, now we can calculate the accuracy and precision, accuracy of our cross-validation result, because we have set 9 different parameters to choose from for this KNN model, where you go through it and you can find, if you're using different parameter, you can see a different final model accuracy or final model performance. So you basically try to choose the best based on your cross-validation result. In this case, it looks like the K equal to 5 performs the best in our model, where you can print out the number, the best accuracy for our K model. And I will not click wrong here, but you can click wrong it. And so that's basically try to do the parameter tuning for the random forest model. And here there are more moving pieces. You can switch back and forth. So to be consistent with our notebook, I only changed 2 features or 2 parameters. One is the maximum number of the band that you want to use for this classification for each tree. So here you can say I want to only use 2 band to do the classification for each tree. And you can also do that. I want to use all of them for each random forest. And then you can also separate the size of your node for each classification model. And this, if you run it, that might take you about 3 to 4 minutes. So you might just wait it. And I promise it works. I tried it on different people's Google accounts for like multiple times. And then with that, we will evaluate the model performance. Looks like the best performance is also, there's combination of those 2 parameters here, the number of the samples that you use for each tree, and not the number of samples, the minimum. Yeah, the minimum number of samples means the smallest leaf you have on your tree. Basically, is the end of your random forest model. And then the Y is the maximum number of the features that you can put into your forest. And so here, that gives you a heat map here on what's the best performing model, a combination of parameter, and then you can then choose your final model based on that. I've been talking a lot, and I just want to double check, make sure that everyone is okay. And I do not see the chat keep jumping up. And any of you have seen any chats people have?
I think you're good to keep going, Johan.
Okay, Ben.
I haven't seen any new
Okay.
questions come up, and Annie had to step out for 1 second, but
Okay, sure.
I'm monitoring.
Right. So this tutorial is once you choose your parameter based on the cross-validation results, and then you can try to start to evaluate your model performance based on the confusion metrics that we just have for this for the binary. And we can compare 2 models we have. One is the k-nearest neighbor, KNN, and also one is a random forest. So in the random forest, that you can see there's slight higher performance compared to the k-nearest neighbor. Again, this is because like these 2 class, forest and water, it's really easy to separate them. If you just look at it, and one is green and one is blue. And so that you can basically easily separate them. That's why overall, both models have high performance. So it's really hard to improve based on that. But then if we move on to the multi-class classification, that's still that we are doing, we have 5 class in this case. And we can try to, for the sake of time, that it might take a little bit longer to train the random forest. So I only train the k nearest neighbor in this multi-class application. And based on this cross-validation code that I wrote, and it gives me the number of neighbors as 15 as the best parameter for the model. So now we can train the final model based on this, and then provides a model evaluation for the confusion matrix for this multi-class classification. Well, when you look at this confusion matrix, and the darker the green means the higher achievement for that class, the high accuracy for that class. The lighter, the paler the green color means there's less sample, which means that it's less. We focusing on the diagonal of this matrix, where it means that we classify those samples correctly. And when you look at, oops, I need to change the code a little bit for the class label here. That should be forest, and let me fix it really quick. So we start with forest, which is first class, and second class is corn, and the third class is soy. The fourth class is urban. The fifth class is water. So you do the same thing for the X label and Y label. Yeah. So just when I think that everything is perfect for this notebook, then this happens, which is acceptable. So we have, and I only correct one, and you correct both of them. So when we rerun this, that should give us the correct, ta-da, confusion matrix that we have from forest to corn to soy to urban to water. So what we're looking at here is that there's a big confusion between the corn and soy. That's something that we're, at least for people who have done classification or know this two cross before, we will expect that this two type is really hard to separate if you only have one time of image. But if you have time series, that because they have different phenology, and then you can get into more better classification for these two different crop types. So here shows there's some thing you can improve for your classifier. So what I would ask you to do for this tutorial is that since you have learned all KNN and random forest, now this last activity is trying to modify the code that you have run through in this tutorial for this classification problem, and try to generate a random forest, and then to see if you can get a better classifier for this multi-class classification. And that's all the content for the classification tutorials here. And I think I'm gonna pause here for some questions or feedback. And please do not leave just yet. Even if you think you're done with the tutorial, you know everything, I have some feedback I want to collect from you. So that concerns about our future tutorial development. So if you want to hang on for a couple more minutes, that'll be great. And also for this session, we have 21 minutes left. I think what I would like to do right now is to open another Slido. And what do you think? Do you think that we should wait for 5 minutes, let people to run through the tutorial?
To actually, well, maybe that's worth a question.
Somebody's
Are people truly interested in running through the tutorial right now?
Thanks, Sophie. And I just want to have a quick like thumbs up, thumbs down. So do you want to keep running tutorial or do you want to have some discussion? Okay, somebody said they are not
Let's
quite
see.
done yet.
Yeah, I will say when I went through it, it took me more than 5 minutes to truly, I mean, you can click through, but
I
to
see a
think
lot
about
of,
what's going
A lot of
on.
people looking for discussion, I think.
yeah, I think more people are wanting for discussion. Sorry, you, Salvas, you are outvoted. But I will always be available for this 2 weeks. So if you have any questions regarding the tutorial, please let me know that I can walk you through like different parts. But I'm gonna go back to my slides. Well, I don't think I need the slides just yet. So it's another Slido. So I want to collect in the feedback before we move on to the discussion. So here you should see another Slido link opened, and it's the same Slido link, Slido website, slido.com, and then you're using ESIP ML with the number 2 as this code for this Slido. And you can also just scan the QR code if you are tech savvy. I really do not know how to scan the QR code without WhatsApp open, so not for me. Now I just opened the first question. So first question is a general feedback. Do you think this session and tutorial useful? And if so, and we have follow-up questions on what's in the future you want to see for the tutorial. Okay, I'm gonna give like maybe 1 more minute for this question, since we have now 35 people in the room comparing to originally 44. Thanks for your feedback, and I think I'm kind of selfish to not put some like negative feedback in the in this choice. Okay, I'm gonna move on to next, and I want to have like 15 minutes for our discussion. So this one is word cloud again. So what future tutorials are you interested in using? So like if you have any specific models or specific application in mind, like the air quality, I heard some like really interesting discussion in the air quality section, cluster session yesterday. And anomaly detection is one. And if you want to know deep learning, that's something that we can think of. But that good thing about Google Colab is that they also have the GPU, so that can can accelerate a lot of like development and also tutorials, which is really nice thing to do. Oh, I saw a lot of like people interested in anomaly detection. Oh, machine learning ethics. That's interesting. Full classification of image. Okay, great. I think that's something I definitely want to work on, because right now it's because for the sake of efficiency for a tutorial, I do not put the image in it, but it can be easily used to image if we have the model already, just adding a couple more sections on the bottom of the tutorial. I'm gonna give 1 more minute for this part. Okay, for the sake of time, next question. The last question is what classes and groups do you think that we should work with? Because in the development for this, I have learned some lessons is that co-development with people who might be interested in using it can be really helpful, because I spend a lot of time trying to figure out what data I should use. At the end, I become selfish. I'm just using Asheville data because I already have the data, and it's really easy to just plug the data in. And I'm also doing a lot of training with my own institute for machine learning. That's why I just use the same data for this machine learning cluster one and for my own training at my institute. So if you want to link us to the classes and groups and fields, that we would be really appreciative about that. I'm gonna give 1 more minute for this part as well, since answers trickle in. I saw environmental sensing. I definitely want to check out with the environmental sensing, because I heard a lot of things about data fusion between those sensors and also some other larger scale observations, which is some of my current research as well. And I saw 2 questions. First question is from VT. I'm just not trying to read the name. For regression, can you perhaps describe an advantage of AI regression methods versus more traditional statistical regression approaches? Okay, so the AI-based regression or the machine learning-based regression, so it do not make assumptions for a lot of those data transformation. While we are doing those generalized linear regression or linear model, that sometimes you are trying to make those assumption of how you need to transform your model to then put them into somewhat linear regression. So that's one thing. So basically, it try to learn the relationship from itself. And there's some really powerful AI-based regression models. If you want to check it out, which I would say is the cubist rule-based regression, which is basically what I did my PhD research on. So it helped me a lot try to get a high accuracy estimation for a regression model. So there are also those like gradient boosting and ensemble-based regression that also follow the same idea that multiple model can outperform just single strong model. That's usually what a single traditional statistical regression approach use. No problem. And I have other questions. I think at this moment, I would say if you want to open your mic and also just like talk, and will be more interactive instead of just me talking all the time.
I just typed it there. But
okay.
Really, it's like, is it possible to leave, like some pixels unclassified because it doesn't meet the criteria of, your training?
There are. So,
and how do you do that?
You can get the probability of belongs to each class, and so as long as you get those probability, you can decide whether you want to leave some of those low probability pixels out. You just say this doesn't really make any sense to any of those classes. You just like say I do not. You can say there's unknown classes that you can do that.
Unknown.
Yeah.
And you say this is possible with let's say random forest random forest. Okay.
For all the classifiers, you can output the probability. So once you have the probability, you can decide whether you want to keep them in there or not. It can be easily done in Python and R. Basically, just like you want to specify them to output the probability, not the class. So Jackie, do you want to ask your question? If you don't want to speak, I totally understand that as well.
Hi. So sorry, I just missed the chance to add into Slido. I was just requesting if you could cover feature selection and potentially unsupervised feature selection in deep learning in any future iteration of this tutorial.
Yeah, sure. One thing I have in my mind is autoencoder. So that's something that that's not really feature selection, but it's one of those like good things to know, and also it have been used a lot recently. I know it's for like quality control for anomaly detection. That's one thing, and then deep learning is one thing that I definitely want to cover. like the convolutional neural network that have been used a lot, and then also the long short-term memory network, which is a long short-term memory neural network, which LSTM is one of the popular and high powerful recurrent neural network. I think Ken has a question. Ken raised his hand.
Yeah, I was just curious about doing some more tutorials or something on time series, but one-dimensional. Seems like most of the machine learning type tutorials are about picture analysis. And
yeah, okay.
So most of my work is more time series based.
Yeah, so for the regression that we did not put in here, that for today is that it's focusing on the single station measurement. So it's time series from one station for multiple years. I believe that's something you would be interested in that.
Like a one-dimensional time series?
Yeah, at when you say one-dimensional, you mean?
So like one temperature measurement at one station over time.
Yeah, so that one I'm using the USCR and US Climate Reference Network. I'm trying to build a relationship between soil moisture and weather parameters. So there's temperature, precipitation, and other solar radiation. Try to build those models for that specific one station, if that's something you're interested in.
I see we have.
You already have that?
I do have that, but I did not release that in today because I don't want to confuse people. So I will definitely send you, if you can shoot me an email, I can send you the notebook, and I will release everything through the GitHub by the end of the summer meeting, because then everyone can access it.
Okay, thank you.
Sure.
I see we have a question or comment from Ken.
I think Ken just asked that.
Oh, that was Ken. Excuse me.
I saw a question from Rennie directly sent to me. Do you want? Oh, okay. You said you are co-chair in environmental sensing. That's great. So yeah, we definitely can collaborate between environmental sensing and
cool.
Machine
Yeah,
learning.
that'd be great. Yeah, I just wanted to put that in there. Also, I'm be pretty interested in that example that you just talked to Ken about.
Okay. Great. More work to do. Any other questions?
Yeah, I'll ask one since nobody. So this is more, you know, sometimes like you have this remote sensing image, you have all those classes, but you're interested in particular one feature. Let's say I'm interested in water one, okay? So I want to classify only water. I don't want to select training sample for a forest. I mean, I don't see it. So do you have some opinion, idea, like what method I should be choosing? I only want to choose one class classification.
Yep, there are during a master, I mostly focus on the land cover classification and vegetation phenology. So some of the work that we did is just focusing on one class classifier. So basically you just have the label for one class and all the others are just unknown classes. So basically you just try to find out that. And so there are some easy way to do it, which is the threshold method that they're also one class classifier in machine learning that you can use. That if you can send me an email, that I can point you to some literature for that.
I will definitely send you that email.
And I think now we have 7 minutes left. I'm gonna say we can still have like 1 or 2 more questions, and then we need to focus on the 3 takeaways for the session.
I'd like to ask a question about how do we use this machine learning to do community structure analysis? Like, for example, in the forest, there are some predators and prey, and they are affected by the environmental parameter, but they also affect within each other. So how do we use machine learning? Because so far the example I saw, it's more like there's only one final dependent variable.
There can be multiple dependent variables. So that because for our current tutorial, it's only a single output, but for the neural network, for like all different type of machine learning models, most of them can produce multiple outputs. Neural network is a really classic example that you can have output layer, you can have multiple outputs. So one of our current project working on is to retrieve the profiles of temperature at different level of the atmosphere using one model. So that's something doable. And some other thing, because you have so many things interconnected in your data itself, so I would encourage you to look into some models like the structured equation model and things like that that can capture those interconnections or interactions between different terms as well.
Okay, is there any other than structure equations, any keywords I can search into?
I cannot think of it immediately, but if you want to shoot me an email, we can have a conversation. Like,
sure. Thank you.
Sure. So someone sent me a chat about the anomaly detection that we do not cover in today's tutorial, but it's something that we will develop. I'm thinking to develop in the future for the tutorial using the autoencoder for some anomaly detections, if that answers your question. And Jackie just put something in the chat about the redundancy analysis can be a nice way to investigate how environmental features explain variances within biodata. That's something I did not know before. Thanks, Jackie. And so now we only have 4 minutes left. I think we need to focus on the takeaways. So I'm gonna, again, here that the link to the tutorial is public, it will not change, and the tutorial will always be there. And now let's look at our Kiko chat. And also I have in the notes section that there's there's a suggestion.
I guess I have a question. Nancy Hobel-Heinrich, are you there?
Yes. Yes.
Hi.
Hi.
I was just wondering about putting this into the clearinghouse and what that actually means and where people might find it through the clearinghouse.
Well, what Johan is going to be giving me some information about, some metadata basically about the tutorials, although I can also gather a lot of it from looking at them, looking at here and looking at it online. But it will be searchable through the clearinghouse by either Johan as an author or by the title itself, by the it's keywords that where the kinds of data that he's using in the examples and that sort of thing. So if you go, it's not added yet, but once I get that information, hopefully by the end of this week or next, then you could just go to dmtclearinghouse.esipfed.org and search for it. And I can drop that in too. Let me drop that into the chat, and then that's something it'll be available there as well as other things related to the topics.
Yeah, I still owe the information to Nancy, and then send me an email. I want to create a Google form the Google Sheet to have the information for both of the tutorials. So yeah,
I think what we would do is have, I think given we want to have a record for both of them because they're different enough. It sounds like that people may be looking for either classification or regression, and as a way to learn machine learning. So it makes sense to do that, a little more exposure. And the thing is, the clearinghouse is all of the metadata that's in there should be available through schema.org and Google. So if you just do searches, once it's in the clearinghouse, if you just do searches for Yuan's name or for machine learning, you should be able to pull them up as well. You don't necessarily need to go to the clearinghouse because you've got them indexed in that way as well. So hopefully that'll work.
Nice.
Yeah.
Thank you.
Mm-hmm. Thank you for asking.
I think we are at the top of our session time, not the top of the hour, but we have 1 minute left. Any lingering questions or comments?
I'm curious if anybody has a takeaway that leaps to their mind. I would love to hear that. Does anybody have a particularly salient thing that they got from today?
Yeah, it was, like very informative to learn about this machine learning using earth science data. Most of those, like you had mentioned in the beginning, it's about cats and dogs, which is fine, but so this gives you easy route to, like, okay, I can relate to this, like I've looked at it, I've seen this data, so I think it's good for a lot of our scientists. So that was my takeaway.
So I'm just adding a takeaway that machine learning in earth science is not the same as machine learning in
cats and dogs.
Machine learning of cats and dogs. Okay, got that.
And there's a good comment by Salvi's in there as well, which was reiterated by Renee, that does the same kind of thing. So in a different way. So that two takeaways there, I think.
So the point would be we need more non-trivial need more non-trivial tutorials in the earth science domain. Did that capture that?
Yeah.
I think definitely those like co-development with people who have the problem, want to use this, and would be a really good way to go forward.
That's true. Yep.
They have the data that we want to provide help to create a tutorial so other people can benefit. That's something can be really, I think is a good model to go forward.
Well, yeah, so that's a good point. I mean, the lab, kind of a lab environment or a collaboratory environment of developing these things would be a great thing to have available too.
Yeah.
Yeah, that's nice.
It may be useful to show like a pair of models, one developed using standard tools and another that takes into account spatial autocorrelation and regression.
Oh.
And show how accounting for spatial relationships can improve model performance. Because we want to demonstrate how, what's special about geospatial machine learning.
I'm sorry, could you repeat that and say that one more time, please?
Yeah, so for example, in a data science, spatial data science class that I teach, we tend to look at pairs of models. One model is done with standard, let's say, scikit-learn over spatial data, and another model is done with the addition of explicitly defined neighborhood relationships or with rasters, and then we can show how that improves model performance.
Just adding the spatial or temporal information into the model and try to showcasing that the model performance can.
That's one. Yeah, that's one approach to that. Another is to yes. So when you explicitly add spatial structure, how that would improve the model. Second is how you demonstrate how spatial data science model are different from non-spatial. And basically, I think you mentioned that was a great introductory part in the beginning, that taking into account spatial bias and auto regression would be helpful. So a specific demonstration of that would be actually great to have.
Yeah. Thanks.